Hey, what is up guys, NVAS here and welcome to another episode in Code with NVAS series. The problem that we're going to look at today is called the majority element, and it is the last problem in the easy set that we have. I didn't do this problem because it has a premium subscription, so we jumped into this problem, majority element. So here's the description of the problem. Given an array nums of size n, return the majority element. The majority element is the element that appears more than n by 2 times. You may assume that the majority element always exists in an array. So they've given an array and we're supposed to find out the element that occurs more than n by 2 times, right? So if there is an array of element, if there's an array of size 10, then this element occurs at least 6 times, right? More than n by 2 times, right? It's the floor, more than the floor of n by 2. So if we have 10 elements, then n by 2 is 5. So more than 5. If we have 11 elements, then n by 2 would be 5.5 and the floor would be 5, right? The int value of 5.5 is 5. So you'll have at least 6 elements which are repeated. So you want the value of that element. So in this case, you have 3, 2, 3. The output is 3 because 3 is repeated twice, which is more than 1.5. Or the floor of 1.5 is 1, which is more than 1. And here in this case, you have 1, 2, 3, 4, 5, 6, 7. So 7 elements. So n by 2, floor of n by 2 would be 3. So the number that is repeated more than 3 times is 2 here. And it said that you may assume that the majority element always exists. So it is guaranteed that there will be at least one element which is more than n by 2 size. Which has a frequency of more than n by 2. And given constraints are n is equal to nums.length. Okay, what is n? N is num. Okay, so return the size of. Okay, fine. And the size of the array is between 1 and 5 times 10 power 4. So which is, there will be at least one element. There will not be any array which is having 0 elements. And the value of nums is given, which is negative 2 power 31 to 2 power 31 minus 1. Okay. And follow up is, could you solve the problem in linear time and in over one space? Alright, let's not jump into the follow up yet. Let's try to do the original question and see if we can jump into the follow up. So the first attempt I would think of when I see questions like this is I somehow keep track of how many elements, I'll keep track of frequency of every number. So now I start with 3 occurred once, and then again 2, so 2 occurred once, and here 3 occurred twice. So I'll keep track of that. And one thing I can think of is you cannot have more than one majority element, right? So if you have n elements, then you will have only one element which is occurring more than half number of times, right? Because half is the equal parts, like one full is having 2 halves, and a majority element is the element which is more than half, right? So which is more than half, then you cannot have another element which is also having, whose frequency is also more than half. So there will exactly be one element which with n by 2 frequency. So the first thing is I'll probably do a counter. I'll keep track of how many elements have occurred, how many number of times, and I've been given only the list. So first thing is I'll take length of the list. Okay. I'll iterate through the list to find out the frequency of every element. And if frequency of any element is greater than n by 2, or I would say int value of n by 2, then return that element, right? Because we've established that there can't be more than one most frequent element or one majority element. Alright, so let's write it. I'll have element counter, which is a dictionary. Okay, for num in nums, I would have if num in element counter. So if I already have that in the dictionary, I would say element counter of num plus equals 1. Okay, so I'm incrementing the value of that by 1. Else, if I don't have it, element counter of num equals 1. So it is a straightforward word count logic. So if I have that element in the dictionary already, then I'll increment the value by 1. If I don't have it, I'll add a new value, right? Now here I would say, like after doing that, if element counter of num greater than floor of n by 2 would be n by 2, right? So floor of n by 2 would be, in Python, it is given by n//2, which is the integer division. And I would have, if that is the case, I would simply return num. A straightforward case. So the moment I find, okay, fine, I'll have to define n. N equals len of nums, right? So the moment I have an element which is having a frequency of more than half the size of the list, then I would return that element. I would return that number. So this looks straightforward to me. Let's try to go ahead. Let's try to go ahead and write some test cases. So for 3, 2, 3, we expect it to be 3. If I have 2, 2, 2, only 2, then also it should pop up right away. 2, 1, 2. It is same as the previous case. 2, 1, 1. What could be the edge cases? If I have only one element, that is possible, right? It should return that value. And n by 2 would be 0. So the moment I read 1, I would return 1. And that makes sense. And if I have an even number of elements, 2, 2, 3, 3, this does not have a majority element, so it's not a probable case in our given scenario. Like, according to the given condition, they said we can assume that there will definitely be one majority element. So this test case is wrong. So this one should be more appropriate. I'll go for another one where I have 3, 2, 2, 2. So my last 3 elements are the majority elements. And then instead of having them in a sequence, I'll have them in a random place. So I'll have 1, 2, 3, 2, 6, 5, 2, 4, 2, 1. So how many 2's do I have? 1, 2, 3, 4. And how many elements do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is not a majority element. I'll have to have more 2's. 2 and 2. Now I have how many? 6 2's, right? 6 2's and 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So for this case, my output should be 3, 2, 1, 1, 2, 2, 2. Okay. And what if I don't find any element which is having more than n by 2 frequency? Will that ever be possible? When we are making an assumption that there will definitely be at least one element which is majority. I don't think so. So we will definitely end in this value. Okay, just for the sake of completion, I'll say I'll return -1 if we don't find any majority element. Just, we can see if our test cases fail. Instead of returning none, we would get a -1. Okay. It looks fine to me. We have a dictionary. We've created a dictionary. We have value for n. We have num and nums, element counter. We are incrementing it if the element exists. If not, we are adding the element. We are verifying. Okay, let's go ahead and run. So all the cases are accepted, all the front end cases that we thought of. Let's go ahead and run the back end cases. Alright, so this one's a straightforward answer that we dealt with, and we did not use the O of 1 space constraint here because we first wanted to get a solution. Now that we got this one, okay, I'll put the entire thing in comments. This one is, what is the time complexity? It is a single pass, so the time complexity is O of 1. O of n, sorry, my bad. It's not a constant time. If there are 100 elements, it is 100, and if there are 1000, I mean, if as the number of elements are increasing, then the time will increase linearly. So the time complexity is O of 1. And as it comes to space complexity, the worst case we can have is O of n again. So because you'll have one space for one element. Let us say you have 1000 elements and you have 499, you have 500 unique elements. Okay, one element in each space for first 499, and 501 elements of 500 times the 500th element. So there you have like how much space you would need. You would need to store 500 keys and 500 values, right? So that is O of n. So O of n is the space complexity. Now he wants us to find it out in O of 1 with O of n. Okay, so how do we do it? So when he says the time is supposed to be linear time, then the only thing is you should be in a position to do it in a single pass, right? But how can we do it without taking extra space? One thing I can think of is not linear time. One quick way we can do it is try to sort the array. Okay, if the array is sorted, then one thing we can make sure of is, like, in any sorted array which is having a majority element, the center element will always be that majority element, right? I mean, this is something that I was able to think while I was explaining the concept of majority element. So when you have, even in the case where I told there are 500 unique elements and 499 elements are occurring only once, and the 500th element is occurring 501 times, even then the middlemost element, which is the 500th element, is that majority element. So when you sort it, it doesn't have to be exactly in the second half or in the first half. It could be anywhere between the first half and the second half. It could spread across both the halves, but the center element will always be the majority element, right? So if we can go into that O of n log n time, then I think you can easily identify which is the majority element. Again, if we assume that we can modify the existing array, right? So let's try to go ahead and write that one. Okay, how are we going to do it? Okay, I'll send this one down. So here I would say sort the list, identify the middle element, right? So if there are 10 elements, what would be the middle element? It could be like 5th or 6th. I think 6th. It doesn't make a difference, right? If there are 10 elements, you will have to have 6 elements which are majority. I mean, the majority element should appear 6 times. So if it's appearing 6 times, if it is the smallest element, then the 6th element will still be the majority element. If it is the largest element, then the 5th element will definitely be the majority element. If it's anything in between, it will definitely be in both 5th and 6th positions. So I can just go for the n by 2th element and return it, right? So first thing I can do is sort. How do I sort in Python? Is it in place sort? Will it return values? Sorted nums equals sorted of nums. This is exactly what I believe is how you sort in Python. I can go ahead and double check it. I'll print the sorted element and the original element just to make sure whether it sorts the existing array or whether it just sorts it and returns it. I mean, will it modify the existing list or won't? It looks like it doesn't modify the existing element. So it would sort the array just like the way we see here, 1, 2, 3, 4, 5, 7, and it will return the sorted one. So it will return the sorted list. So this is a correct approach. And I would return sorted nums of, okay, I need a variable to store the length. Not mandatory, I can just use the len function even in the function, but it kind of looks neat. And by 2, right? //2. So that will be the middle element. This should work. I'll sort the array, I'll get the length, and I'll return the middlemost element of the list. Are the test cases passing? No, they're not. List is not callable. Oh, crap. Sorry, syntax. Okay. It passed. And if we submit, it is successful. The time complexity for this one is more than the previous one, because in the previous case all we were doing is just running one pass along the list, so it is O of n time complexity. But here we are sorting the list, so the best sorting time complexity we can arrive at is n log n, other than some special conditions. But here, assuming it's a general case, it would be n log n. So the time complexity for us in this example is n log n, and the space complexity is O of 1, right? Because we are sorting, ideally it is O of n in this specific case because we're duplicating the array. But I'm sure we can, given some time, we can write a logic where, we do in place sort of the array and then find the middlemost element. So it would again be, the space complexity would be O of 1 or could be O of 1, and the time complexity is O of n log n. But how can we do it in O of n time complexity? So we need something which is, best of both worlds. We need that to happen in a single pass, and we need in constant space. Well, I have one solution, but it does not seem appropriate to me. The space will still be constant. No matter how many elements we have in the array, we will create an array of size 2 power 32. Okay, so the 0th element would store the value of negative 2 power 30, the frequency of negative 2 power 31, and the 2 power 32nd element would store the value of 2 power 31 minus 1. So you have an array filled with all zeros. Okay, and when you have 2, then the corresponding element, which is at the position 2, will increment its counter. So it is sort of like a hash map, but with constant space of a list, which totally doesn't make sense, because you're sticking to that logic, you're doing it in a single pass, and you are using constant space. O of 1 doesn't mean you're supposed to use only one element, but it is like you are supposed to use the same amount of space regardless of how many other elements you have. Even if you have one element, you use the same space. And even if you have 5 times 10 power 4, how much is that? 5 times 10 power 4, 5,000? 50,000 elements. So even if you have 50,000 elements, you're using the same amount of space. But I think 2 power 32 minus 1 is a big number, somewhere around, 7. How much is 2 power 31 minus 1? 2 power 32? Oh, this is, okay, it is a huge number. It's 4 billion, right? So it is not an exact solution that is, efficient, if you ask me. It uses constant space, but it's not, we can definitely do better. I just don't know how. It somehow feels like we can use some concept related to dynamic programming or memoization, but I just am not in a, I'm unable to get to that. I'm unable to see through it. It's a hunch. It feels like I can use dynamic programming or something, because usually in questions like these, you will be somehow, in a position where you can break the problem into a smaller problem and solve it. But are there any hints given? No hints. Only the topics. Divide and conquer, array, bit manipulation. Oh, okay. So bit manipulation is similar to the concept that I explained before, the array concept, where you have an array of size 2 power 32 and you would store frequency of each element. We could probably have how much? Instead of having those many elements, you could make one 8-bit number or 8 numbers into a single byte, right? If you have 4 bytes, that is 32 elements. 32 zeros, right? Zeros and ones. So even then, it is difficult to find out the most frequent number, because you could have an element which is repeated 2 times, but there is no way you can add that into the counter. Arrays is a concept that we have used. Divide and conquer. Can we do divide and conquer? Internally, when we are sorting, even though we use the existing internal function in Python, we are using divide and conquer, but bit manipulation is somehow, I can't see through it. Okay, let's try to look at the solution and see if we can understand what he's trying to do. We have the brute force approach. Yeah, this is the exact same code that we've written probably. Right, we have majority count is num by 2 by 1 in okay, and for each number, okay, this is not what we've done. This is O of n square complexity. So what he's doing here is he's taking one element, he's going iterating through the entire array and trying to see how many times that element has occurred. If it is more than n by 2, he's returning that value. If not, he's going to the next element and he's doing the same thing again. So for each element, he's doing an entire pass of the array, right? So that is n by n square complexity. He has a loop inside a loop, and he's iterating through the entire array for each element of the array. So this is crazy. I mean, yeah, I didn't think of this. It didn't come to my mind. I mean, even though this was one of the easiest things, and if you would have given me this question like 4 or 5 years ago, then I would have definitely gone for this, because at that point of time complexity was something that was completely foreign to me, and the only thing I was bothered about was to get a solution. So right now I'm thinking of writing code which is scalable. So this doesn't make sense to me in a straightforward way. I mean, it doesn't come to my mind right in the first bat. Okay, this one is out. Time complexity is of O of n square, and space complexity is obviously O of 1, because you don't have to store anything new, right? The second solution we have is this Hashmap. This was the solution that I thought of when I started writing code. Hashmap is the dictionary solution that we have. That is the one that we have here. So initially he's populating the Hashmap here. This is the main function, the majority element function. Initially he's populating the Hashmap, and then he's going through each key, and if majority entry is null or okay, so he's just trying to iterate through every element in the hash map and find out the element with maximum frequency. Okay, so I didn't think of this because I was assuming that given a majority element, its frequency will definitely be greater than n by 2. So I didn't do the second pass. All I did was I said if the frequency is more than n by 2, then return it directly. It would seem to be working even in this case, and I think it's going to match all the border scenarios as well. So we didn't do this one. The time complexity and the space complexity is O of n and O of n that we've discussed. Sorting. Okay, this is something that we've done as well. Okay, wow, impressive. So he is in the elements if the elements are sorted in monotonically increasing or decreasing order, the majority element can be found at n by 2 or n by 2 plus 1. Okay, well, I'm patting myself on the back. So I was able to think through this. So the majority element will always be in the middle. Yeah, this is this solution. Which one? He sorted it. Arrays.sort is an in-place sort, which is having space complexity of O of 1 and returning the middle element. What did he do in Python? Oh, we have a nums.sort which does it in place. I don't remember this. My bad. So nums.sort does an in-place sort. So if I instead of this, if I just say nums.sort, it would do an in-place sort where we are no longer using a duplicate element. So we don't have to assume that sorting is in place. It is in place. Space complexity would be 1 and returning the center element. That is good. Randomization. Okay, this is completely new. Time complexity is O of infinity and space complexity is 1. Much like the brute force solution, the randomized approach runs with constant additional space. Okay, this seems a little complicated when I look at it the first time. Let's try to go deep. So majority count, okay. While true, you randomly chose one element. If sum, okay, this is a sort of like a list comprehension. 1 for elim in nums, if elim equals candidate greater than majority count, return candidate. Okay, so he is randomly choosing one element from the list. Since it is random, you wouldn't know which element he is choosing. It doesn't have to be, it's not biased towards being the first element or last element or the middle element. You're randomly choosing one element, and then you're iterating through the entire list. That's what he's doing, right? For each element in nums, if element equals candidate. So he's iterating through the entire array, and if the element that he randomly has chosen, which is candidate, is same as the element that is present there in that position of the array, then you're incrementing some value to 1, right? And ultimately when you sum them up, you have, if there's a match between the element that you've chosen and the element that is in that position of the array, you're getting a 1. If not, you're getting a 0, right? So when you're doing that, when you sum all of them up, if the value is more than n by 2, then the frequency, it is the element which is having a frequency of more than n by 2. So the majority, which is greater than majority count. So he's returning the candidate. Okay, this is something that I would never think of. Okay, let's see the complexity. It is technically possible for this algorithm to run indefinitely if we never manage to randomly select the majority element. Of course, because randomness, even though it's not truly random, like for example, we have 100 elements, like if I assume the 1000 elements frequency, and what if the random number is always selecting that unique elements instead of the one? Because when you're doing a random selection, you're not ruling out, like, if I've already selected this number, don't bother. We're not doing anything of that sort, because if we have to do that, then we'll have to keep track of what elements that we've chosen randomly, which will add up to space again. So we cannot do that. So we're going through each element, and it's stateless in a way. Like when you're randomly choosing one element and doing the entire process, you're not verifying whether that element has been processed before or not. It is stateless. So for every random choice, it acts as if it's a new one. So it is possible that it can indefinitely happen. However, the expected runtime is far better, linear. Linear route. The expected runtime is linear for the modified problem. Therefore, the expected runtime. So it is something related to the concept of expectations in probability, expected value. So the concept, if someone's really good at this concept, maybe he can think of such solutions. Which is like expectation is defined as sum of all the probabilities of a probability and its frequency. Okay, and the space complexity is 1, and the divide and conquer approach. Okay, this looks crazy right in the beginning, and its complexity is also O of n log n, which is similar to, which is same as if you're sorting the array, and the space complexity is log n. Okay, we have something called Boyer-Morse voting algorithm. Okay, maybe this is the algorithm that they're looking for. I'm pretty sure it has that O of 1 and O of n and O of 1. See, O of n and O of 1 time and space complexity. So what is this algorithm? If we had some way of counting instances of the majority element as plus. Okay, let's not get into this algorithm in the video. I think it'll be a really long video when I do that. Since I'm just looking up at the solution, it probably doesn't make sense for me to read it out loud and try to understand it and explain it to the video. I'm pretty sure there are several videos outside which explain what this Boyer-Morse algorithm is, and I'm pretty sure I'll include this in the Algo with NVA series someday and try to code it. So yeah, that will be the end. This is something that I've tried today. Like instead of just going through a problem and solution, I'm trying to do it in different approaches. Like trying to do in one approach and trying to make it better. Because the question demanded it, I thought of it in that way. And I'm trying to do the time and space complexity. And in the end, we are going through each and every solution and trying to see what we've got and what they're trying to explain. That's what we have right now. So that's pretty much it for this video. If you like this video, make sure you hit the like button. If you want to watch more of these videos, then hit the subscribe button. And if you want to get notified every time I make a new video, then make sure you hit the bell icon. Alright, that's pretty much it. Thank you very much for tuning in. I'll see you in the next video. Bye.